This video is going to tell you all about how to graph a derivative and how to find out if a graph or a function is differentiable. When you're graphing derivatives, what you have to remember that derivatives are tiny, tiny tangent lines. And tangent lines, the way that we found those was by using the formula of slope. So we're actually going to be looking at tiny little slopes and figuring them out all along the graph to graph the derivative function. Sounds complicated, but I promise I'm going to break it down for you. The thing you have to remember is that you're looking for slopes of the graph you're given. So I'm going to come over to my function and I'm going to draw a tiny tangent line. So let's say I want a tangent line right there. What kind of slope do we have down here at the end? It's going up and to the right, so that means it's a positive slope. And this slope is pretty steep, so this is a big positive number. And I'm just going to move my way along. Now this is a tangent line, still positive going in this direction. Might be a little less steep than down here, so I'm going to make this plus sign a little smaller. Then I'm going to keep going up here. Again, positive slope. But as I keep going up, these slope lines are getting less and less steep. And look what happens up here at the top. We have a straight line. What kind of slope is up here that is a straight horizontal line? This is a zero slope. That slope is zero at a horizontal line. Now, as we descend down the graph, here, what kind of slope do we have here? Now we have a negative slope. Notice the direction of the line. That direction is negative. And then we're going to get down here. And look, this guy's a little steeper than up here, so he's getting a little bigger. And then notice right here, look how steep that little tiny tangent line is. So that guy's pretty big. Then he's getting a little less steep. He's also still negative, getting a little less steep. And then notice what happens here. Again, we have a horizontal slope, which means that's zero. So notice it gets steeper in the center here, but then the negative slopes get a little smaller, right, coming to and from zero, which should make sense. Now we're going to go up to the right-hand side. So again, as we go up this way, what kind of slopes? We have positive slopes. This is a small positive slope. This slope is getting a little bigger because the line is getting steeper. And notice this is going to get real big. So the first thing you have to do when you're graphing a derivative is you need to write on the function you're given, what kind of slopes do you have? Are they positive slopes? Are they negative slopes? Are they zero slopes? Is it a big positive? Is it a small positive? Because now we're going to turn around and graph our derivative. We're going to use these pluses and minuses and the zeros to graph our derivative. The first thing I recommend is marking a few key points. Look at your zeros first, look at your highest negatives and your highest positives, and let me show you how that works. First with the zeros. This spot is going to have a zero. Well, where's zero? This is where y is zero. So these pluses and minuses are your y values. We have another zero, right? It comes right up here. And all I'm doing, if you want, you could even draw a dotted line to make sure it lines up correctly, but I'm marking my zeros first. Now, as I start to the left side of my graph, I have a big positive. So I'm going to go straight up from here, and I'm going to put a dot at a big positive way up there, all right? Now, as I move left, I have my big positive, I have my zero mark. Right in here, right on the y-axis, we have our biggest negative value. So I'm going to put a dot down here at our biggest negative value. As I continue to keep going, I already have my zero marked, and my slopes over here continue to get more and more positive. So up here, it's really, really high. It's a big positive. Once you have these key points mapped out for your graph, now all you need to do is go ahead and connect those dots to draw your function. We're starting at a very high positive number. We're coming down We're hitting through 0 right here. We hit our biggest negative at the bottom. We come back up through 0 and back up here through our high positives. And of course, you put arrows on the end. Now, is my graph perfect? No, but that's okay. You get the general idea and the general shape. And if you see, the blue graph was an x cubed graph, and the green is an x squared graph. You're taking the function that you're given, you're using tiny tangent lines, tiny slopes, to graph the slope of the derivative. Let's try a couple more examples. Here's the function. We're going to start with the function on the left. So again, I'm going to draw tiny tangent lines. Well, this guy is kind of flat, right? He's kind of close to 0. He's not exactly 0 because we know these kinds of lines continue and get closer and closer to that x-axis. So we know that he's not really 0, but we know that he's heading that direction. Now look right in here. What kind of slope do we have? That's a negative slope, negative. So these I would say are probably tiny negative values. And then we go down here and this guy's getting real big. And this guy's getting real big. And these slopes are almost straight up and down. But we have that negative tilt to these ones. Now I'm going to graph the other side here. And we go to these ones. And I'm going to kind of start, because these lines can be so vertical and horizontal, I'm going to start right here in the center. And this kind of slope is a positive slope. And this guy is a little smaller positive. And again, these ones are closer to 0, but we really know they're tiny positive slopes. And this guy coming down here, he's positive. And this guy, right, these are getting big positive slopes. Now that we've graphed the tiny tangent lines to see if they're positive or negative, we need to put some key points on our graph. As we look at the left-hand side of this function, look, little tiny negatives to big negatives. So you want your function to follow the same thing. Because if I start up here at little tiny negatives, right, here's some negative values, and then it gets bigger, right? This is actually following the same kind of pattern as this one here. We don't just want to go negative and draw a straight line. You want to follow the slope of the graph. So this function itself will actually look the same as this one over here. But now if we look at the graph on the right-hand side, these are tiny positives. Okay, these are y values. So tiny positive y values are going to kind of be up here, and then they get steeper and steeper, and so all the way they're going up. So this part of the graph is going to come down like so and head up here. So there's our derivative for that function. Let's take a look at the absolute value function on the right-hand side. This one's going to get interesting. I'm going to start again with graphing tiny tangent lines. So when I do tiny tangent lines, these are all negative slopes. And notice, this is a straight line. So these negative slopes are all the same size. They're all constant. Now let's look at the one on the right. These slopes are constant and these slopes are positive. They are all the same value because the slope is exactly the same in this kind of straight line. So what does that do for our graph? Well, on the left-hand side, we have a constant negative number, and on the right, we have a constant positive number. So a constant negative number would look like this, with an open circle on your y-axis, and a constant positive, and it looks like the slope is the same, only one's negative, one's positive. So I'm going to go about the same distance up here and do a constant positive. So this would be the derivative of an absolute value function. Now let's talk about differentiability for a minute. Differentiability, differential, those mean the same thing. So let's talk about what that means for a function in a graph. If f of x is differentiable at x, that means that the derivative of the function exists at x. If f of x is not differentiable at x, then the derivative does not exist at x. I'm going to give you some graphic examples to show you what that means. What you're trying to find out is if the function has a derivative, if it is differentiable. So we're going to again look at the tiny tangent lines and the slopes. If you look at these slopes right here, they're going negative, right? These are all going negative. But when you get down here at one point, you can't find a slope because you need 2 points for a slope, right? And then all of a sudden, these guys are going positive. So at a cusp, you will not be able to find the derivative. A cusp is not differentiable. And if you look over to the graph over here on the corner, right, with the absolute value function, the one that we just graphed, we found out these were constant negatives and these were constant positives, which made your graph look like this. And therefore, that limit of that function doesn't exist. If you can't have a limit, you can't have a tangent line because the tangent is the limit of a slope. So if you have a corner, again, it will not be differentiable because there will be a break in the graph. Let's look at a vertical example. Again, we're talking about tiny tangent lines. What happens right here, this vertical piece right here? Well, when you're trying to find a slope of a vertical line, a slope is your y values divided by your x values. But all your x values are same on the vertical line, which means you would have 0 in the denominator, which means you cannot find the derivative of a vertical line, making vertical lines, parts of graphs, non-differentiable. Because you can't find the slope of a vertical line. And if you look over to the graph on the right, the one that is discontinuous, hopefully you're all seeing right now, you can't find the limit of a discontinuous graph, which means if you can't find the limit, you cannot find the tangent. That one would not be differentiable as well. Therefore, you have 4 spots at least where graphs and functions will not be differentiable. That is the cusp, the corner, if it's vertical, or if it's discontinuous. We're starting at a very pi has